Hello, in this video we're going to learn how Le Chatelier's principle can be used to explain what happens when pressure and volume changes take place to an equilibrium. Now recall from the ideal gas law that pressure and volume are inversely proportional. So that means if the pressure goes up, we can also think about the volume going down and vice versa. If the pressure goes down, volume we can think of as going up. Very important. Let's consider the equilibrium between N2O4 and NO2. You can see that as N2O4 breaks down in a reaction to form two molecules of 2NO2, we can think about this equilibrium. There's an equilibrium constant for this, 0.0059 at 298 Kelvin. And that means this is pretty strongly reactant favored, so you're going to have a lot more reactant. So you're dividing by that number, it's pretty small. But what we want to know is what happens if you were to change the pressure. What happens if you were to increase the pressure to the situation? Essentially, what would happen if you were to change the volume, right? So if you increase the pressure, it'd be like reducing the volume. Here's a little video to help you think through it.
A sealed flask contains 3 molecules of nitrogen dioxide for every 1 of dinitrogen tetroxide, and the system is at equilibrium. If we then transfer the mixture to a flask with a smaller volume, NO2 molecules convert to N2O4 molecules, resulting in a net decrease in the number of molecules. In this way, the system compensates for the decrease in volume by a decrease in gas pressure.
So there's a shift in the equilibrium when the pressure increases. Now the pressure has to be increased in a way that affects essentially the concentration of the reactant and the products. You can't just add something in there that's not a part of the equilibrium and expect it to change. So it's important to think about how is the pressure being changed. So in this situation here, if you were to increase the pressure, the gaseous system here will shift to the left to make less moles, thus decreasing the pressure of the system. So less moles, less pressure. That's the ideal gas law. So this is a shift left. So one of the big concepts is to learn which way will it shift. So if you reduce the volume or increase the pressure, okay, the way you would increase the pressure in this situation would be to add maybe more of something, one of the molecules in the system, or changing the size of the container. Then increased pressure, reduced volume is going to shift left, and the vice versa. If you were to expand the volume, increase the volume, that decreases the concentration of everything, more room for more moles, and it'll shift to the right. So in this particular problem, but you got to shift to the side with the most moles, most number of moles. So you got to look at the coefficients of your reactants and your products. So that's the conceptual part of it. Does this really work mathematically, or is it just sort of a concept? You can better believe that there's a mathematical explanation for this. Let's look at it now. So let's consider the Haber-Bosch process of nitrogen plus 3 moles of hydrogen to make 2 ammonia molecules. Let's say the equilibrium condition is with all gases at 2 atmospheres. This is incorrect, but we want some easy numbers to think through this. So that means you could calculate the equilibrium constant by going, okay, the product raised to the power of the coefficient there for ammonia, so that's 2 squared, and that's divided by concentrations, or the pressure in this case, of nitrogen raised to its power, the coefficient's 1, and then hydrogen raised to its power, which is 3. So it ends up being 4 over 16 if you do the math, which reduces to 1/4, which as a decimal is 0.25. All right, so what happens now if we were to increase the volume, and that means we would increase the volume means you're expanding the system, the pressure all goes down. Which way would it shift? Well, if you're at half the pressure or twice the volume, let's think about what would our new initial situation look like, our non-equilibrium situation. Well, that means everything would be cut in half in terms of the pressure. So instead of being 2 atmospheres, it's 1. And so when I would look at the initial, or this non-equilibrium condition, I can do a Q calculation. I just plug in those pressures, so back into the equilibrium expression, And you can see that I end up with a Q equals 1. Well, then I go back and compare it to K, and I say, oh, well, 1 is greater than 0.25. So that means if Q is greater than K, I have to shift away from the products. So it's going to shift left. I have too much product at this situation now, and so I'm going to shift to left. And that, consequently, actually goes right with our concept of, hey, if I'm reducing the pressure, I can shift to the side with more molecules. Well, the reactant side has 1 mole of nitrogen and 3 moles of hydrogen, so that's the side that has 4 moles compared to the side that has 2, so I can shift left. And if we were to set up an ice table to solve this problem, we'd put our new initial non-equilibrium pressures of 1 atmosphere across the board, 1 atmosphere for nitrogen, 1 atmosphere for hydrogen, 1 atmosphere ammonia. And then in the change line, since I know now it's going to shift left, I'm going to increase the reactant, so I'm going to add the change there. And the change goes X for nitrogen plus 3X for hydrogen minus 2X for ammonia, since that's the product and it's going away. And I can set up a new equilibrium line, 1 plus X for nitrogen, 1 plus 3X for hydrogen, and 1 minus 2X. Now, when I'm doing this initial line, students are often thinking, well, how come I don't use 3 times this or 2 times the ammonia to put those initial values in? Well, those are the actual pressures. We just put them in. The stoichiometry shows up in the change line, 1x, 3x, minus 2x. That's where the stoichiometry comes in. I can set up my new equilibrium expressions, or new equilibrium expression with these values, and I can plug it in and solve for it. I keep K the same, K will not change, and I would solve for X. Now, this is actually turns out to be a really hard one to solve, and we probably won't see something like this on a quiz or test for general chemistry, but we could solve it. It's solvable, for sure. Not a problem. We could work it out. A lot of X's, probably X to the 4th power in this one, so we need some advanced algebra here to solve it. It could be done. So we're just not going to do it here. The idea here was to figure out which way would it shift. How would we set up the ice table? How would we think it through? So the shift then, the Chatelier Principle, helps us decide which way this is going to go. And hopefully you can see that now. Now, did the equilibrium constant change when there was a pressure or volume change? No, it doesn't. Equilibrium constant stays the same. We just get a shift, and we got to see how the pressures now, or the concentrations, readjust themselves with the shift. Here's an example question to see if we can use all these concepts of concentration and pressure volume changes. Suppose we have the following reaction at equilibrium, PCl5 going to make PCl3 and chlorine gas. Each of the following statements is false. What if you added PCl3, one of the products, to the container? Will it shift the equilibrium to form more PCl5? Is that true or false? How about decreasing the volume of the container? Will it shift the equilibrium to form more PCl5? Well, what if you remove the reactant PCl5 from the container? Will it shift the equilibrium to form more PCl3? What do you think? Let's go back through them and think through it. A, adding PCl3 to the container shifts the equilibrium to form more PCl5. That is correct. That is true. So PCl3, that means I'm adding more product. It's going to shift to the left to make more of the reactant PCl5. So that's true. That's good. How about B? Decrease the volume. So my quick concept that I go to, if I'm decreasing the volume, I'm increasing the pressure. I want to shift to make least amount of moles. So that is the reactant side in this case, because there's only 1 mole of PCl5. See, there's 2 moles over here. So this is our heavy mole side. This is our least mole side. So decreasing the volume is going to shift to the side with the least number of moles to make more PCl5. So that's true. So probably by default C is false, and that is correct, because if I take away PCl5, the reaction wants to shift to the left to make more PCl5, not PCl3. So here's the answer for that. And hopefully you've learned a little bit more about pressure and volume changes and some questions that could be asked, and how to think about setting up ice tables and all these wonderful things about disturbing equilibria. That's the end of this video.